Amazing. It's been 5 hours and we're back and we're doing another stream. This is crazy. I don't know why I'm doing this. This is crazy. But you know what? It's so much fun. It is actually quite a bit of fun. Yeah, I struggle with stuff. I don't know whether I should explain the things I'm doing or just jump straight into doing it or like whatever. But you know what? Life is short and we only get a few chances to do what we need to do. And yeah, so we're gonna push as hard as we can, as far as we can, and then we'll see where it goes. For sure. Cool. So yeah. Yesterday in the previous register, talking about register already. In the previous stream, well, not in the previous stream, in yesterday's stream, when I was working in yesterday's FPGA stream, we managed to actually put a small CPU on this Arduino FPGA, and I'm gonna boot it up and we can see it in action. It should be a Blink CPU. And that's it. It just goes red, blue, green, red, blue, green. Yeah, I'm a real streamer. That's what Bartholomew says. I mean, it's cool. Yeah, it's just life, man. It's just life. Let's see how it works. I think it's actually quite interesting. And yeah. Okay, cool. So let's see. It's definitely not boring around me. There's always something to do. So let's just jump into the code because Bartholomew is here, and if anyone else shows up, they can ask questions and stuff. So we have this CPU that we made yesterday. Yeah, we have this CPU that we made yesterday, and it's a very simple CPU. All the CPU does is it's sort of like it has two instructions: increment and output. That's the two instructions that the CPU has. Now, these two instructions are cool, but what I want is to build a RISC CPU, and a RISC CPU that follows the RISC standard. One of the RISC CPU. Let's see, RISC CPU. Yeah, reduced instruction set computer. That's what I want to build. Okay, cool. And I'm just building this so that I can learn how like the stuff works, and then we can go forward with it. But one of the first defining features of a RISC CPU is that it has, the key operational concept of a RISC CPU is that each instruction performs only one function. So we already have this already. Each instruction only performs one function. That way you can run instructions quickly and use many instructions. That's kind of the concept behind RISC CPUs. Okay, cool. So now, the next part is that the RISC computer usually has many 16 or 32 high-speed general purpose registers with a load store architecture. What is a load store architecture? This is all complex words to explain something really simple. This thing has multiple general purpose registers, and when you're using this thing, you do what is this part? You have a load store architecture, and a load store architecture means you're either loading from memory or you're storing from memory, and then you also have another you have two sets of instructions. One set of instruction works with register to memory or memory to register, and then another set of instruction works with register to register. So you have like stuff that you do with your ALU. What is an ALU? When you're doing logic or you're doing arithmetic and logic unit. Yes, if you're adding, if you're minusing, if you're multiplying, if you're dividing, all of those things. So let's see. So that's sort of the defining features of a RISC CPU. And what our tiny 8-bit CPU does is it has one program register, and then based on that program register, it just does some instructions, and that's what we're seeing here. It basically sets one thing, increments it, sets one thing, increments it, and at some point it sets the bits that matter to these LEDs flashing, and then we see them. But what I want to do today is I want to just do that next minute step. I just want to add multiple registers to my implementation, and then once I do that, I can actually once I add the multiple registers to my implementation, then we can think about the next part, which is doing like a load store architecture where we will just go and copy like the open RISC instruction set. They have an instruction set, yeah. So the open RISC instruction set. Well, this is the one we'll try and use. Okay. So where is, they have an instruction set that we will use. I have not researched this. I have not gone and read on this, but I will read about it and then we'll see. But what I'm saying is, that's the next step. Today, all we're doing is just making our code work again, but now with multiple registers. We're just adding one tiny feature. And I wrote some notes for doing this. I wrote some notes for doing this. Here they are. By the way, let me just do this quick and add the stuff to let me add the link to these notes on the video's description. And then I want to put this in the video's description. Let's top. And then, so multiple registers to the 8-bit ECU, and then I think there's a Discord server in there and everything. So yeah, you can join the Discord. It's in the description. You can look at the notes there in the description, and so on and so forth. And then the code we are working on. Is there a link to the code that we're working on? 8-bit CPU. Yeah, for sure. That's fine. At some point, this thing is going to become a 32-bit CPU, but I don't know when. It's fine. Okay, cool. So the current state is that... That's not cool. It's status. Oh, no. I lost some notes. I genuinely lost some notes, and I am very scared. Holy crap. Let me close all of this. I just want to make and Vim do this thing again. Oh no, it's ghosty. Pardon me, let me pull up some notes quickly. In the meanwhile, if anyone has questions, please ask them, and Bartholomew will laugh at me. But yeah, the documents, and vim.u, and then if I go in here and I go to the bottom and I say this, and then I say recover, enter, G, yes, git status, git add, post. I feel like we do this on every stream and I should stop. Nah, this is real, man. This is just raw. This is not a video. We're not doing a video. We are just working in front of people, and this is normal development. Git status, git commit -- amend. Say hi if you're on the chat so that it's not just me and Bartholomew hanging here. I can see a few more people offline or online. I mean, git push -- force. Yeah. Please let it load up. But I can also read it from here. But it's kind of harder to read on Markdown while we're doing. Well, Markdown. It's not really that hard because I render my Markdown, so it's fine. So let's see cd documents, and then I'll go into HDL, and then I'll go into tiny CPU, and then we are here git status. This is where we were yesterday. Amazing, cool. So let's drop in some stuff. Let's quickly go, and number one, let's see if our code is loading so that we can just read it from up here. Yeah. Yes. All my notes are here. Okay, cool. So I'm going to read notes, jump back to the coming. So cool. So the first thing we're going to do today is just move this into multiple what the heck? What did I say? My cats are fighting. Move this into multiple general purpose registers. So let's add them. Let's make them 15 instead of 16. I will close this because this has been updated, so we can just stay. Yep. So we can just stay here, and then I can say that, and then we can go into main.v. Let's edit this. Let's edit this very low. So the first thing we do here is we can actually get a hint from the fourth line below, and you can do R, and then we can go here into R. We can say R is of size Y. That happens every string. R is of size 0 to 15. Amazing. So what do we have here? We now have 16 general purpose registers. Okay, so this adds 16 general purpose registers, and that's it. We're done. No, not really. We actually broke everything. It won't even work now. But yeah, let's fix it. Let us go ahead and fix it. Okay, so the next thing we do is the problem with going to 15 registers or 16 registers is now the end. There's a bit of our code that runs on A. So our CPU checks register A. So it's going to break here. And our RGBs, our RGB LEDs, they also power up based on register A. So register A is a 4-bit value, 3-bit value, and if depending on the bit that's been set, depending on the bits that have been set, the LEDs will light up. Okay. But now we don't have register A, so now we need to come up with a different way of knowing, because we just added many registers. So the next thing we need to do is to come up with a way of knowing which register the instruction belongs to. And if you recall, our registers here, they have all this blank space at the end. See? The least significant 4 bits are just basically blank space. Everywhere it's zero, because the 2 instructions that we have are increment and output. It's a placeholder. It's not do anything really. It's just a placeholder. So we run the cycle and we get an output. So that's all we have right now. So the thing I'm thinking, and what is conventionally done if you read up on the RISC documentations, is that we use this part of the instruction. Is it the instruction? Yes. These are plain instructions. This is basically our code. So this part of the instruction, let's actually add some documentation in here so that we can always understand what is happening here. So and then it doesn't like that. And then it's you. Alright. So let's do that. Oh my word, it's so hard. But I actually like it this way. Yeah. So these are placeholder instructions. Before we have to deal with our compiler. Okay, so before we have to add a compiler. Okay, right now these instructions, they are like the instructions. Upper. Is it upper? What is it? Is it upper word? Upper 4 bits. I feel like this is a byte or something. 4 bits. opcode, and then the lower 4 bits now become the register to use. Okay, so let's use this lower part as addressing, you know. So let's now start using this lower part as addressing. So basically we're adding addresses here. We're just counting, really. We're just counting, you see. We're just counting on the lower part. It's quite easy, yeah. So we have a possibility of 16. So there can be 0, 0, that's fine. And then this can be 1, and then 1, and then this can be 1, and then this can be 1, and then this can be I think let's do, this is 1, 1, and then this is 1, 1, and then this is how do I count? Does anyone know how to count from binary? It's, yeah, because if you flip them, it's become 100, and then this will become 100, and then this will become how do we say? And then this becomes 1, 0, 1, and then this becomes 1, 0, 1, and then this becomes so the 1 flips, it flips the next one, so this becomes 1, 1, and then this becomes 1, and then this becomes 1, and then so the 0 flips, it becomes 1, 1, 1, 1, 1, and then 1, 1, 1. Yeah, so we just counted to 7 basically. We just counted to 7 basically. We just counted to 7 in binary. That's what we did. Cool. So this actually fixes quite a bit. So the 0, 0, 0. So our opcodes right now is 0, 0. These are 0, 0, 0, 0, 1 inc and 0, 0, 0, 0, 1, 0 out. These are our opcodes right now. We'll add more. Not today. We'll add more. So what we've done here is we basically fixed this new problem. We basically fixed this new problem where we don't know where we had one single purpose, one general purpose register. Now we've added 15 more, so we have 16 general purpose register. So now we've fixed the problem so that we know which register the program counter, or rather the instruction, is pointing at. Okay, that's basically what we've done here. So anyone who has any questions? We're almost done. It's insane how quickly this goes. We're almost done. The next part is the complicated part, but it's not even that complicated. Tell me if anyone has any questions. So now we know. I'm checking. Okay, cool. No questions yet. So previously our code was like this, and this is just fine. We would check the upper 4 bits for what instruction are we going to get, and then based on that instruction we would do something. We would change A or we do nothing. It's like a NOP. It's like a NOP instruction, no operation instruction. So now, because we don't have A, what we need to do first of all is we need to find out which register to use. So we need to, you see this is reaching into, wait, where's my mouse? Where's my mouse? I think my mouse is dead. So this is reaching, this here, this ROM here is reaching into the ROM array that we have over here. Okay, so in the same vein, we need to reach into the register array that we just created, and I have some. That means I've streamed enough. If my mouse dies in the middle of a stream, that means I've streamed enough. So what we need to do is change it to this line. And it works just the same as the case. So we need to get into the register array, and then we need to pick the address that we're going to be using. So the lower, is it the lower? Yeah, we need to pick the lower 4 bits because that's going to be choosing the address that we're going to be using. So let's pick that, and then we go from there. I hate it that my mouse is dead. Oh, it's back. It's back. So that means I need to go and charge it. So in here, we need to reach into R, and then in R, we need to pick ROM, and then in ROM, we need to do PC, and then here we need to do, it's 3, 0. So the last four bits, that's what we need to pick. The last 4 bits tell us, you see all this counting we did up here, the last 4 bits tell us which address that we're using. Okay, that's cool. That is exactly cool. So that's how the code looks. Yeah, it ends with 2. Yeah. Now here again, we need to do the same thing. This is the non-blocking assignment operator. It enables us to run code asynchronously. And all we need to do here is we basically increment a value and then we mask it by 111. So this value is this A is this address, this one, this first 4 bits. So I think we're gonna pick that one. No. Yeah. Okay, so instead of, yeah, it's just A again. It's just A again. Look, let's remove this. Let's do, am I going into ROM or R? Yeah, it's just A again, ROM. And then in here, pick program counter. And then in the program counter, let's pick 3 and O. So this is the register that we need to increment. Is that really it? That really is it. So we just replaced A instead of statically addressing A. Instead of statically addressing A, what we just did is we picked A from wherever we wanted. That's cool. So we've done an operation. Now, what we need to do is fix our, you see there's still an A here. So we need to access this A, but I need to think about it. Do we still just replace it the way we did it up here? I feel like that would be too simple. What do the notes say? Same thing. We just replace it the way we did it up there. So most of my stuff was just reading today. Okay. ROM and then PC and then is this 3? Oh, so we're only using that in one place. Okay. Fair. Fair. Okay, so in the PC we need to pick 3, 0. Cool. And then I can actually add that, that's fine. And then here, same thing. R, ROM, PC, 3, 0. That's fine. And then in here, it should be 1. But this is 2 here, so it finishes on the right place. And then we can remove that. Okay, cool. And then here, it's also R, and then we pick into, we step into ROM, and then we do PC, and then in here we pick the 3 to 0, and then in that finishes that, and then in here we need to do, now that finishes that, and then here we want to do 0. Is that what my notes say? I kind of wrote that from memory. Yeah. Selected register. So this is just a selected register. All of the way here, this is just a selected register. And then we check the index. Or rather, yeah. And then we check the index that affects this the index that affects this this LED itself. And I think that's it. I really think that's it. Okay. Yeah. Yep. Verilog people use tabs, so I'm gonna learn how to use tabs like them. So, and look at this up here. Verify. Is it verify? No, it's up here. Lint. Let's see. Let's see. I found a way of making it work because previously it wouldn't work because, oh yeah, we don't even have a lint error. Oh my word. Okay. up your build. Warning, replacing read-only memory with list of registers. C main V61, V41. What is happening? What is wrong there? Is this because it knows what was the 41 to 61? Yeah. I've never seen that error. This is the first time I'm seeing it. Some Verilog thing should come up from Starcraft. No? Okay, it's fine. So I think Verilog here is telling us it's doing something. This is fine. So this is the first time now we're now becoming actual Verilog developers. So let's see, what does that mean? We discovered the error of the stream. It was gonna end in 20 minutes. We discovered the error of the stream. Come on. That's cool. Let's see. Name is not doing anything. You're setting one byte to 0 but never reading its value, and then reading another byte that you're never setting the value of. So the synthesis tool is replacing it with registers instead. So what have I done? What have I done? How have I messed that up? How have I messed that up? I might have not messed it up. It might be just that it might just be that we've Verilog can see something we can't see, and it's just deciding to optimize away. So we are like really the first time this is kind of something we might, if we wanted it to do something, if we understood enough that we wanted it to do something else, we would use something like volatile or something. So main V61, main V41, see main V61, 61, 41, 61, this is 60, oh, okay, 61, okay. Is it saying I'm not doing anything, or is it saying this read is irrelevant, so I'm not using it, so it's not even like choosing to do something with it? Or this is from the cheat sheet. So ROM 61 41. It doesn't like that I'm doing that, but I'll go and ask at work and we'll see. There's a lot of like what do you call it? Verilog beasts at work, so they'll tell me Control R and then I think ice prog. Is it RGB blink? No. Ice prog build hardware, build default hardware. Bin. So I'm gonna hold it up. I haven't even typed it in, so let's paste. If they come back and they blink, it worked. I'm super scared right now. I promise you. So it's going red, 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 red. I wonder if it will ever roll over. And oh yeah, it rolled over. It rolled over. Now it's blue. Roll over. I can let me disconnect it so it goes again. See, it rolls over at some point, goes red, 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 and then at some point it rolls over, goes blue, blue. And I bet you at some point it will roll over and go to green. It never rolls into green. It never rolls into green, and it never stays. It goes like red, blue, red, blue, red, 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 blue, red, 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 red. It doesn't even matter. Let's see. Wait. I have a feeling. I know what is happening here. These are not all the same instructions. So 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. And then this is 0, 0, 0, 1, 1, 100, 101, 110, 110, 111. There's something I'm doing wrong, but I don't know what it is. But what we have discovered is we have multiple general purpose registers for this thing. Does anyone have any questions so far? I think a half an hour stream is also okay. I'm okay for doing that. It's also weekend. I've sort of managed to do something really quickly, and I'm kind of impressed by myself. So I don't have to make it a longer stream. That some of my streams go like an hour more because I'm trying to like debug something, but I don't think I'm gonna do that because it's working. And we are going to have an opportunity to do something next time, so that we'll have something to fix, we'll have something to go on with. But this is just mostly here so that we can we can learn and fix stuff and do stuff together and all of that. And I think this is it. I really think that's it. I don't see any errors. And I do not have the intuition. To see what is broken right now, because all of my information comes from like just reading the cheat sheet, the very long cheat sheet, and just doing it. If anyone has ever read the book, Learning Python the Hard Way. Learning a programming language the hard way is just typing every instruction you can read from the programming manual. Just type it and see what it does. In the beginning, you will not know what you're typing. In the beginning, it'll just feel strange. You will look at it and it'll be like nothing. Even a new concept that you're learning. Try it. Bartholomew can tell you. If you want to learn math, you want to learn FFTs, just do them. Do as many proofs as you can until you get to a point where you get enough neurons connected in your head and you can see where it's going. But before the neurons connect in your head, it's going to look strange. It's going to feel nothing. Okay? Oh! No way! So, What book? The Python book or what? There's this book. This is the book I just referred to. Learn Python the Hard Way. It's a book. It's just I don't do Python. It's one of the things that I don't do Python, but it's a good. I tried to do it, but yeah. But the thing is if you just go into something and you start typing and you start trying stuff and you try stuff and you try stuff and you try stuff, it just becomes, at some point, it becomes At some point, you start realizing what is happening, and then when you start realizing what is happening, you start making connections, you start building context, you start building intuition. And that's mostly what I do on these streams. I go do something that I don't know, and then I practice it, and then with each successful stream, with each successive, not successful, with each stream that comes after the other, I learn something, and I imprint it in my head. And it's way easier. It's way easier. Just read it, fail at it, just try it. Try it from start to bottom. Do the sum from start to bottom, get the wrong answer, do it again, get the right answer, and then notice why you got the right answer, and such on and so forth. It's going to green, man. It's going to green. Oh my god, it cycles through all of them. But now it's like some shade of green and yellow or something. So it's mixing up the colors. And now it's blue. Now there's no red. Anyways, that's been a super cool stream. Thank you so much, number one, Bartholomew, for coming to hang with us. Thank you so much for all the other people who showed up but didn't comment. And yeah, cheers. See you tomorrow, where we review our FIR implementation. I don't know that it's right, but I'm gonna try it again. Bartholomew, did you check it out? You can comment. At some point, I need to add a video call to Bartholomew so we can just like be talking on the stream, and it can become a podcast anyway. Yeah. So tomorrow we'll review that. We'll review our FIR implementation. We will test it with actual noise because now it's working. And then in the evening, we'll probably look at something like an arithmetic and logic unit. That has been a very successful stream. We've done something. We've added the feature that we wanted. We need to write a commit for it. We need to write a commit for this, and then we're done. So that's what that works. Git status. Git add main git diff -- staged. Okay. Yeah. Git commit -m. This is RISC v move RISC move towards RISC implementation with multiple registers. By the way, git push. It's so cool because if you look at ARM usage fault example, it makes you understand so many more things. So let's see a usage fault. When you see a usage fault, you know, ARM usage fault, and if you've looked at many of these, you know, you actually know where I'm going with this. Yeah, something like that. I should use my own blog where I've worked with, like, I want to see a usage fault. Yeah. No, not that one. I would like to see a usage fault. Here's a usage fault. Somewhere. There's a fault. But if you notice, my word, come on. There's a, like, the classic one. I need to get a better computer. If you go and look at a usage fault, you will realize, or any sort of like good fault, it's here. We can look at it. You see how many registers are here? It's R1 to R12, but usually there's 15 of them. There's usually 15 of them. Why? Something about... Come on, just give me a usage fault. Just give me a usage fault, man. Image. Let's look at images. That's fine. One usage fault. No, not I can make one right now, but I don't want to make one because I don't want to. Let's see. Do I have an example on my blog? GDB explorations. Please give me some sort of usage fault somewhere. Yeah, no, it doesn't. Anyways, if you look at an ARM usage fault, you will realize there's R0 to R15, and it's 16 general purpose registers, and you can look at them, and then you can start looking at, because now we know what these registers are. You see, if you know which register, you can look at each of the register and you know, like, okay, this function called this function, and then this function returned an error. So, let me actually just attempt one more. Let's find an example. It's this. This is somehow messing with me. ARM usage fault example. Yeah. If I can just get one. If someone just posts their ARM usage faults, we'll be okay, and we will actually see a RISC CPU in action. Nah, I don't download anything. Yeah. I think I just saw one. Look at this one. I think I just saw one. Someone's yeah. Cortex M fault. So Cortex is a RISC 5. I don't know what ARM is based on, but what you have here. No, this is just now like actual. Anyways, I give up. Yeah. I give up. But what is happening here is if you manage to make a if you manage to find Cortex usage fault. I can't believe the thing that was hard today is how to find a usage fault, like an example. Please tell me you posted your actual usage fault. ARM hard fault example. Basically, you usually get, it usually shows you. Do I just make one right now? Yeah, let me just make one. Let's make a quick usage fault, and this will become really clear. This is easy. Yeah. I don't know what you want. What are you complaining about? There's 3 cats behind me, and they're really complaining. They're mad. CD. Let's actually make a usage fault so quickly. I think I know of one existing one in CD Zephyr samples I2S drivers I2S LS I2S codec boards. Yes, CD I2S 2S codec West Control R activate clear West build dash B STM 32 F4 disco dash P. Always, this should be a small example, so it should build quickly. Yo. So let's just say what I want to show is the 16 general purpose registers, so that we see we're actually going towards making a CPU like the CPU on this board. Okay. And then once we see them and we get the epiphany of like, yeah, it actually looks like that, then we can say bye, and it's been an hour of streaming and it was fun. And it was fun. Fun as heck. Did I push my code? I think I pushed. Did I push? Did I push my code? West flash. I need to get a thing, yeah. Cool. Let's go here and then we can do Control R screen. Yeah, maybe. Yeah, probably. And then that's fine. West flash. Is it? I don't get. No. Whatever that did. Dash R open OCD. That's better. I don't know what STM programmer did, but like that's some bullshit. Yeah, this is connected. This is connected. Control A, K. Yeah. LS dev. Yes, Baba. We're gonna make noise. This is Luffy. So ls dev, yeah, and then let's connect this one. It might be USB 0. ls dev USB 0. Okay, cool. So instead of that, let's do USB 0. And then let's reset this. Look, R0 all the way to R15. There you go. 16 general purpose registers in our production CPU. And then in our code, what did we do today? In our code, what did we do today? 10 minutes ago, what did we do? In our code, in our CPU that we just implemented at home, while not knowing anything, we added 16 registers. So, as an STM32 has 0 to 16 registers, our CPU has 0 to 16 registers. We're becoming RISC. Anyways, thank you all so much for showing up today. That was amazing. It was cool to write code with you today and learning. And I'll check you guys tomorrow when we do something new. Please remember to subscribe, leave a comment or something of this sort. Bartholomew is laughing at me because I'm becoming a streamer. But yeah, thank you so much. Cheers. See you guys tomorrow. Let me know if the code works. Let me know if it goes anywhere. I'll see you guys. Amazing.